SP15. We will continue studying Markov processes, and in previous lectures we have studied that probability of a process, that is a Markov process, the probability at any given time n is dependent on what has happened at n-1 and is independent of whatever has happened before. So the present is dependent on recent past only, right? So given a Markov chain, which is also called the transition probability graph, we can compute the probability of a set of feature events. Set of feature events means that we want to compute a joint probability, right? Suppose we start from time 0 and we go up to time n. We want to find out that at nth time the probability that the process is at state n. Suppose we have n states, and at time n-1 it is at state n-1, and at time 0 it is at state 0, right? This can also be written as that this probability is a joint probability. We can assume this to be event B and this first term to be event A, and we know that joint probability of A and B can be written as the conditional probability of A given B times the probability of B. So this whole stuff from here to here, we call it B, and we apply the rule of joint probability, converting joint probability into conditional probability and this marginal probability, right? Here we can apply this property, Markov property, because we know that Markov property suggests that probability of an event at n is dependent only on one recently happened event and is independent of everything that has happened before. So applying Markov probability, this whole term can be written as this. Right, this whole term can be written as this, only this, and all these terms are neglected because the probability of this event isn't dependent on this these far past events, right? And this term, that is also a joint probability term, can be written as in terms of conditional probability, right? And I haven't written all the terms here because this probability isn't dependent on these far past events. and it can be written and in such a way that we keep on writing terms unless we reach to a point where x1 probability x1 equals I1 given x naught I naught, and then finally we have this initial probability term. Right. In our last lecture, we studied that that probability of ij, that of probability ij is the probability of having xn or xn plus 1 equals j, given, in last lecture we studied that, given xn minus 1 is I. This is what we studied in our last lecture. So on these same lines, this term can be written as, this term can be written as, this term can be written as this, where this is I and this is j. We are going to n from n minus 1. Right, all these terms, probability terms, can be written on the same line. Probability I sub n minus 1, in minus 2, in minus 1, and finally I0, I1. So it keeps on going, and we know that all these terms are conditional probability terms that we can find both in Markov chain or transition probability graph, as well as in transition probability matrix. So all the terms in transition probability matrix that we studied in last lecture and in transition probability graph are conditional probability terms. Right, if we know the initial probability and we want to find out this whole set given this small information, that the first or the initial probability is this, we once again can apply this product rule. Xn, probability of xn is in, given all these things. We can consider this as a and this whole as b. So, and we can apply product rule. A comma b, a joint probability of a and b can be written as the probability of a given b times the probability of b, and we can solve it in the same way like we did before, and we come out with this expression, right? And we have applied this on every step. We have applied the Markov property that the present is dependent only on recent past and is independent of far past events. Right, now we are going to solve an example. This Markov chain was studied by us in one of our previous lectures, and we want to compute some probability that we want to compute this. We are given that the initial probability, that the initial position is 2. This means at time 0, the chain is, the process is at 2. The process is in state 2. And you want to find out the probability that as the time goes on, at time t1, the process is in state 2. We know that once it is in state 1, it remains in state 2 with probability 0.4, right? And at time t2, it's again in t2. This means with probability 0.4, it remains at t2. And at time 3, it goes to 3. It goes to 3 with probability 0.3. And at time 4, the process is found in state 4. This means it goes to 4 with probability 0.3. So we have to find this conditional probability. We want to have this set of events occurring at time 1, 2, 3, and 4, given that at time 0, the process is found in state 2. Right. We can apply product rule assuming this to be A and this whole stuff to be B. Probability of A given B, assuming applying Markov property at the same time, because whatever the probability of the state 4 at time 4 is independent of 2, 1, and 0 and is dependent only on what it was at time 3. So we have applied the product rule as well as the Markov property in one step. X3 is equal to 3 given x2 is equal to 2, and then we keep on writing these terms unless we reach here. So we have written this in terms of these 4 product quantities which are multiplying with each other by applying product rule at the same time, by applying product rule, Control C, product rule and Markov property. Product rule and Markov property at the same time, and have obtained this product of these 4 terms. So this means that we want what is the probability that the process will be in state 4 at time 4 given it was in state 3 at time 3. So there is no time in between from time 3 we jump to time 4. So we see that from 3 to 4, the probability is 0.3. So we'll write a 0.3 here. Right, now we are going to find this conditional probability term. From 2 we go to 3. From 2 we go to 3. From 2 we go to 3. We go to 3 with probability 0.3. So this is 0.3. And then from 2 we go to 2. From 2 we go to 2 with probability 0.4. So this one is 0.4, and from 2 to 2 is 0.4. So we multiply these and find this joint probability, given some initial information that the process was in state 2 at initial time t is equal to 0. Right, now we are going to solve another part, is part B of the question. This is part B of the question. This part we have to compute this joint probability, and we are given nothing. What is the probability that the process is in state 2 at time t is equal to 0, at time t is equal to 1 it is in state 2, at time 2 it's in state 2, at time 3 it's in 3, x4, at time 4 it is in 4. So we'll again apply the product rule as well as the Markov property at the same time, neglecting all these terms that we can write after this x3 is equal to 3, because we apply Markov property and found that this term is independent of all other terms. Therefore we don't write those terms, and we apply Markov property and product rule. We keep on doing that this chain rule unless this chain rule takes us to this point. But this is a conditional probability. We can compute that from the Markov chain transition probability graph or transition probability matrix. This one is also computed from TPG transition probability graph. This one is also computed from TPG, but this term isn't given. This is an initial value. What is the probability that initially our process is in state 2? So this is initial probability, and this should be known initially. This must be known. If we want to compute this joint probability, we must know the initial probability of the process, that initially at time t is equal to 0, what is the probability that it is found in state 2, what is the probability that it is found in state 1, in state 2, 3, or 4. In our upcoming lectures, we'll keep on studying more about Markov processes. Thank you.